Having choppy Zoom meetings for online classes? Or are you scrolling through social media such as Instagram or Facebook? Maybe you're jamming out to music at home, uploading work to the internet? Or is it a restful day for Netflix and chilling? All of these activities are made possible through data transfer and the technology of data compression. Hi, this is Manese. Is my voice clear on your end? It's audible enough? Alright, cool. Let's find out why this is the case with data compression. Before we get into the specifics, it is important to understand the derivation of the subject matter. What is data? Data is simply a raw collection of digital items holding no significant meaning. When these bits of data are brought together to produce meaningful ideas, we then call it information. Data is transferred through codes making use of redundancy to reduce error from noise. However, the amount of redundancy may exceed what deems necessary. Knowing that information is represented through data and processed with redundancy, data compression is the act of reducing said redundancy in data. Before we ask ourselves the question, why do we do this, we need to understand the history of the subject. The history of data compression dates before digital technology. The start can be seen in Morse code developed in 1838, where the compaction of characters were assigned to the most commonly used letters in the alphabet, E and T, having one dot and one dash respectively. In 1940, information theory came around. In short, it was the idea that quantitative information is inversely proportional to its probability of occurrence. In other words, the most unexpected events yield the most information. This opened doors for a magnitude of approaches to data compression. This includes the Shannon-Fano coding and the Huffman coding. The Shannon-Fano algorithms assigned code words to specific symbols based on their probability of occurrence through a series of divisions. These divisions are done as close to half as possible. So in this example, we divide the W from X, Y, and Z because it has a probability of 50%, while the rest sum up to 50%. We assign zeros to the top halves and ones to the lower halves. The top can no longer be divided, so we have to move on to the lower half. We now divide the lower half in two. Since X has a probability of 25 and Y and Z sum up to 25, we can divide it again and then assign our zeros and ones. Lastly, we divide Y and Z, assign their zeros and ones. And finally, we can assume each symbol's code word. Huffman coding is similar to Shannon-Fano coding, but takes it a step further and is able to achieve a more optimal code consisting of shorter code word length. It does this with a bottom-up approach by repeatedly combining the least common symbols until there are only two left. We can compare this to the Morse code from earlier. As we saw earlier, the algorithms displayed try to shorten code words, making our return to data compression. Now, how does data compression actually benefit us? First of all, it allows more storage availability due to its file size reduction, followed by cheaper transmission due to needing less bandwidth, and lastly, it saves us time in transferring data. Of course, with the good comes the bad. The disadvantages of data compression include possible errors in data due to less redundancy and a loss of information. A key concept in compression is the compression ratio. This ratio simply depicts the extent of compression in numerical format. There are limits to how far compressibility of data can reach. This limit of compression is equivalent to the entropy of the source message. Entropy is a measure of uncertainty with the given equation. Looking back on information theory, the correlation becomes apparent. The lower the entropy of the system, the more compressible it becomes. Processes on compression differ based on type and purpose, but two things remain constant, and that's encoding and decoding. Encoding is simply compression at the message source, while decoding is decompression at the destination. I'll now go over the classifications of compression and their respective applications. First off, we have lossless compression, where as the name suggests, the file integrity is perfectly restored upon decompression. Lossy compression, on the other hand, compresses data at the expense of data being disregarded or approximated. This means that a higher compression ratio is used, and we can't ever achieve our original data again. It does, however, have a significantly smaller file size than if we were to use lossless compression. If we take a look at program files being transmitted, we are most likely to make use of lossless compression methods to ensure functionality. You wouldn't use a tool that is incapable of doing its job. Text files or document type files also make use of lossless compression, since missing words or numeric data can potentially cause harm for senders and receivers, especially at a professional standpoint. Images make use of both lossless and lossy, depending on the intent. PNGs and GIFs are the examples of lossless image formats, while the JPEG is a format that makes use of the lossy compression. For example, the social media pages we were scrolling through earlier make use of lossy compression upon uploading above the recommended file size threshold, whereas photography or scientific research would use lossless compression since the quality of images are vital in their businesses. If we take this subject and compress it to a lossless PNG and a lossy JPG and zoom into the sleeve of her sweater, we can see the detail on the sweater is less obvious in the JPEG file when compared to the PNG and the original image due to the higher compression ratio approximating more pixel values. Audio compression takes sound and applies cutoffs at a frequency or decibel level threshold. The most common lossy file type is the MP3 that can be seen everywhere, such as voice recordings, while the FLAC format is a lossless format and is mostly used in places like the music production industry. Videos make use of both image compression and audio compression, which is what's going to happen once I export this video. Most of the time, videos come in the form of lossy compression. This is the case because if you take an hour and 30-minute feature film at HD quality, its lossless file would at least be 100 GB in size, which is way too big for a single film on our disk. An example file type for a lossless video format would be the AVI, while lossy formats include the FLV and the MPG. That marks the end of our discussion. I hope you were able to learn as much as I did and gained an appreciation for the derivation, history, mathematics, classifications, or applications of data compression. This was Manese. Thank you for tuning in.